Here's an easy problem that almost every high school physics student can solve. What is the potential energy of a 1 kilogram rock suspended 74 feet above the ground? That's easy enough to calculate if we know the equation. In this case, potential energy, U, equals mass times gravity times height. So let's run the numbers. The mass of the rock is 1 kilogram, times the acceleration due to gravity, which is 9.8 meters per second squared, times the height of 74 feet, or 22.5 meters. This gives us about 220 joules of energy. Okay, that's handy to do, but it doesn't really tell us anything about potential energy. What is it, and how does it get converted into kinetic energy? Plus, what about gravity? What is gravity? How does it pull us towards the Earth? The equation U equals mgh doesn't really answer those questions. To find those answers, we'll do the same problem again, only this time we'll use the most famous of all equations, E equals mc squared, mass times the speed of light squared. Now this may sound difficult at first, but it's really not, so let's run the numbers. The mass of the rock is still 1 kilogram, times the speed of light, times the speed of light again. And this gives us a really, really big number. This is the amount of energy that Einstein's equation says is actually contained within that rock, and it's not even remotely close to the number we got before. That's because there's one more piece of information we should know. If you placed a perfect clock at both the bottom and the top of a 74-foot tall tower and perfectly synchronized their times, in 13 million years the clock at the top would read 1 second fast. Now this is not due to any problem with the clocks. It's due to the fact that time itself moves slightly faster at the top of that 74-foot tall tower than it does at the bottom. It's true. Back in 1959, scientists at Harvard University proved that time flowed a tiny bit faster at the top of a 74-foot tall tower than it did at the bottom. Now this may seem like a really small amount. Some might even say insignificant. But if you multiply that small difference in the rate at which time itself flows by a really big amount of energy, like the energy in the rock, you get something pretty significant. You get 220 joules. Notice what we did here. We were able to find the potential energy of an object by using its mass and the difference in the rate at which time itself flows. Nowhere did we mention height or gravity. To learn why this works and what it tells us about the nature of gravity, please visit 220joules.com.